Will, it's of course a great pleasure to have you with us to talk about this very important research on the issues of the Earth system, climate change and sustainability. There are many concepts that are somewhat new to most of people, and I would like to ask you to start with about the Anthropocene, this concept that you are very much related with.
Yeah, this is a new concept that really was put forward in the year 2000, so nearly 20 years ago now, by Paul Crutzen, an atmospheric chemist, Nobel laureate as well. There are many, many definitions that people use for the Anthropocene because it's spilled over into civil society, all different aspects of society. But in terms of science, there are basically two. The original one is an Earth system science definition, and that's looking at the last roughly 12,000 years stable state of the Earth system, the last interglacial between the ice ages. And the fact that we are now pushing the Earth system very rapidly out of that 12,000 year stability period. And obviously people focus on climate change, which is very important, but also the biosphere in its own right is being changed enormously. Extinction rates are probably 100 times background and so on. So when Earth system scientists looked at all this, and said, well, this is something really new and different. Paul Crutzen just used the term Anthropocene. Now, that term, when you look at the CENE, scene, immediately tells you something about geology. So, of course, Paul, in his initial interpretation, also meant for it to be considered by the geological community. So the second definition is a geological one. And it's related to, but it's certainly not the same as the Earth system one. And the geologists look down. We look up in the atmosphere and around the biosphere. They look down into the stratigraphic record, the cores that you can drill in soil, ocean sediments, rock, and so on. And they're looking for very clear markers that are globally synchronous that tell us that the entire Earth has changed into something new. And they are undergoing a process now, a very careful, thorough process, which is actually rather advanced. So the Anthropocene Working Group, I think there are 36 people, agree virtually unanimously that this is a real geological phenomenon as well as Earth system, and that it should be formalized in that long 4.6 billion year time scale, geological time scale, and the preferred start date is the mid-20th century, which agrees very well with Earth system science. So these are the two definitions that are coming together really quite nicely now.
So what you're telling us is that, let's put in this terms, in the future, geologists will look to the surface of Earth and we will identify it very clearly from the second half of last century onwards that there is something completely new, that the action of man is so overwhelming that it left signals that are completely new. Is that what you would say? And this is very concrete. It has several indicators from, well, not only geology, but so what you would say to, let's say, the deniers? There are some people that stubbornly think that, well, this is just terminology and it's just a way of keep on the sciences, and this is not very important for most of people. I mean, what you would say to those?
Well, I would say, first of all, that the observations are overwhelming, that there is something new and different. And you can start from the geology. When you look at the cores that the geologists, the stratigraphers, which is a subset of geology, these are the people who drill these cores and look at stratigraphic layers in Earth history. They see so many new things appearing. They see plastics, they see radionuclides, new radioactive materials, some of which will be, for hundreds of thousands of years. They see changes in biological fossils because we're changing the biology of the planet and so on. So I think the real advantage of the geological approach is they can put this into context and say to the deniers, actually, we are the timekeepers of planet Earth. We know the timing and the magnitude of changes that have occurred in the past from the cores that we have. And they have judged, independent of what us Earth system scientists are saying, they have judged that this is very significant, that it's globally synchronous, it's happening right around the world, and it indeed is at least as big as changes at the level of an epoch for example, from the Pleistocene, the Ice Age period, to the Holocene and so on.
That's very striking, right? Yeah. Even I'm a theoretical physicist, and I'm studying the subject for the last couple of years or so, and I have to say it is very striking. So the other concept which I think is key for understanding the state of this emerging science, Earth system, is the concept of planetary boundaries, to which, again, you have given a major contribution.
Yeah, that was research that came, again, out of the Earth system science and resilience science community. And we were asking ourselves the question, now that we have entered the Anthropocene actually isn't a stable state of the Earth system. It's a trajectory. We're moving away from the Holocene. And a lot of people now are making a normative social judgment that this carries very big risks for humanity, and indeed for much of the rest of the living planet, that the changes are so fast and so rapid, they look somewhat like a meteorite strike when you look at the deep past. So the question is, what do we need to do to restabilize the Earth in something that looks like an interglacial, like the Holocene? So we looked at contemporary Earth system science and our understanding of how the planet operates as a single system. So what are the key processes and what are the limits that we shouldn't transgress if we want to keep the Earth in a stable interglacial-like state? And that was really the birth of the planetary boundaries. So it was based on a workshop with about 25 scientists from various aspects of terrestrial ecology to marine biology to stratospheric ozone to chemical pollutants and so on. And I think we were very successful in terms of looking at this incredibly complex system, the Earth, and coming up with what we thought were 9 processes which, at a minimum, could describe the state of the system. And then we've used the historical record and the geological record to try to inform us as to where these limits might be. So the planetary boundaries is, if you like, it's a guidance system for how far we should or shouldn't push the Earth system if we want to keep it in the stability domain. And just to close off here, when we assess where we are now, we have transgressed some of the key boundaries like climate change and biosphere integrity, that is the integrity of the biological systems around the planet. We're changing them too fast, extinction rates are too high, CO2 is too high, and we see it in terms of temperature going up, extreme weather events are changing, and so on. So I think the observational record really does support the planetary boundaries framework and where we are today.
So you mentioned 9 parameters, but it could be more complex than that, right?
Indeed. What we're trying to do is find the minimum number that are tractable. And when you dive in, some of them are multifaceted when you get sort of underneath each one. Yes.
And the change of these 9 parameters, they're all compatible with this idea that the change is far too fast in comparison with all the changes that are related with astronomical, internal dynamics, geophysical ones. Okay, so that's something that one can see clearly from these parameters, right? So the rate of change is very, very quick in comparison with other. And I think it's also a very important point, the time scales. Okay, so this is something crucial for physics. Okay, when you look to some phenomena, right, you say, well, I will make a measurement on this time scale, and on this time scale, atomic effects or subnuclear effects are totally irrelevant. Okay, so but what we are seeing now is a very quick change on a human's scale of time, and that's, let's say, very, very worrisome, put in mild terms.
Yeah.
So this leads us to the most recent research on which you and your collaborators have pointed out that you might be going dangerously into a very different situation in comparison with the Holocene, this hothouse Earth scenario. So could you tell us what are the main scientific signatures of that, and how does it came out of your research?
Well, the hothouse Earth idea came out of using a complex systems theoretical framework. A lot of the contemporary discussion around climate change still is focused on climate as a somewhat linear system. That the more you emit, the higher the temperature goes, and when you stop emitting, the temperature stops. In other words, you can push your system to a new position, like driving a car and you park it and it stays there. But when you look at the recent history of Earth's system and the longer history, it doesn't behave that way. It behaves as a complex system that has somewhat stable states and transitions between them when you get feedback processes enabled and you cross a threshold. So we used this framework to look at where we are in terms of the Earth system. We looked at states of the Earth system in the recent past, like the previous interglacials, like the mid-Pliocene, which was 3 to 4 million years ago. The mid-Miocene was a bit earlier than that. So we looked at these more recent ones because the continents are reasonably similar. The further you go back, of course, the more difference you have to deal with. So we see that the Earth system in its recent past can actually exist in different states. And then we ask ourselves the questions, what are the important feedbacks that can enable a transition between those? And we've identified 10 of those. And then we look at where we are now and in terms of pushing or activating those feedbacks. And when you put all that together in sort of a synthesis picture, you see that we are pushing the Earth system toward a possible domino effect, where feedbacks like a row of dominoes, you tip the first one and tips the next one and so on. That's how complex systems work in a coherent way. So we assess that we could push the Earth system to a warmer state, 4 or 5 degrees warmer than pre-industrial, which we've nicknamed hothouse Earth, that this is very feasible, perhaps even within a century or two, which is extremely fast in geological time. So that's basically the essence of the paper, that we are pushing away from the Holocene. That's what the Anthropocene is. We don't exactly know where this cascade is going to be activated, and that's the real question that gets right back into policy, into social and economic debates about where we're going. And so what we're saying is that we think this is a very credible framework. We have enough evidence from the geological past, from complex system theory and so on, to say we better take this seriously. Now we've got to do more research about perhaps narrowing down where that planetary threshold might lie.
The starting point of this model was precisely the idea that was conveyed by Will, that we lived in a very special period, the Holocene, in which the temperature fluctuations were very, very small in comparison with what happened earlier. And that means that this is a very special place of equilibrium. And any change from that is considered to be a phase transition. And this is tapped with the whole subject in physics, on which you can deal with in a general, very general framework, from transition, for instance, from water in the liquid state to water in a vapor state or ice. So these are different phases of the same substance, water. So here we are dealing with different phases of the same system, the Earth's system. That's the idea here. And the idea is to tap on this general theory of phase transitions. And normally, if there were no humans on the planet Earth, there wouldn't be any human action. And but physics also deals with this. For instance, you have a system that's settled in a state, and for instance, you apply a magnetic field, and it changes the state of the system. And we model the action of man very much like a magnetic field changing the state of the system. And so this term here is the linear destabilizing term of the Holocene. So you have this minima here, which was the Holocene, and once you turn on this term here, you get this black curve, and this point here is the hothouse Earth scenario. Okay? And I can show mathematically this is an attractor. That means trajectories, all the trajectories of this temperature field will go into that. So that comes to the issue of, can we use the physics to stabilize the system? Using Will's picture, I would write the following. The intervention of man is controlled by, let's say, 9 parameters. Allow me to use mathematical language, okay? So it's something that varies from 1 to 9. So these are the 9 planetary boundary contributions to the human intervention. But that's, let's say, if it's within that boundary, the safe boundaries, you remain in a safe region. But you told me something fascinating yesterday, that this is actually more complex than that. And for instance, I can have something, I'll write this way.
Absolute interactions amongst
interactions between them, okay?
Yes.
So I will write them this way.
Yeah.
And actually, there should be interactions of 3 terms. I could
That's
go on that, okay?
Yes.
I could go on that, okay?
Yes, that's right.
Let's say alpha A, J, K, A, J, K, and so on, okay? But let's stay with this 2, okay?
Yeah.
So, if this is true, then you can have, let's say, negative contributions to these interactions, and therefore you can more or less drive the system away from this minimum. And Will, please tell me something about interactions of these parameters, okay?
Yeah, no, but this is a really nice formalization with the 9 planetary boundaries. And you can start to think of it a little bit. We can think in 3 dimensions. If we only had 3 boundaries, you could think of a cube. And we humans are pretty good visually getting up to 3 dimensions, maybe 4. But this is, if you like, a 9 by 9 matrix.
That's right. Yeah.
So it's a 9-dimensional space. But examples of this, let me give you an example of how the boundaries interact. There are 2 of them. Obviously, climate change is an important one. But another one is what we call biogeochemistry, the nutrient flows, phosphorus and nitrogen, which are essential for life. But they also affect how the Earth system functions. So as we change climate to higher temperatures, we're changing rainfall intensity and patterns. And that changes the erosion rate of phosphorus and nitrogen. So that means we have to pull our boundary back on phosphorus and nitrogen. That's just one example of what these interactions look like. But a colleague and I are working on a very simple mathematical approach to looking at what these interactions are, what are the really important ones. Fortunately, many of them are actually close to 0, which is a good news for us, so we don't have to worry so much about them. But what we're going to do is look at our little wheel where we show the 9 boundaries going out as wedges. And if you don't look at the interactions and look at only the boundaries, it's a nice symmetrical thing. But we're going to animate, as we start changing these boundaries, the shape changes. The space, safe operating space, changes in a 9-dimensional way. So this is a beautiful mathematical formulation, and it's actually also very practical, because we can start describing in a simple way what these functions are.
Yeah, I think this is fascinating. Let me use the 3-dimensional picture,
Yes.
which it's close. Well, I draw these in 2 dimensions, but I could draw this in 3 dimensions. Okay, I bring this out, and let's say what's in the board is without human intervention. And now human intervention is in this axis here. So what is our model is saying, and what Will is telling us, is that the human intervention is actually creating a minima around here, so the system goes from the Holocene to this dangerous hothouse scenario if you do not do anything. Prevention, or let's say mitigation, or whatever you call this strategy, would be to work out these interactions so that we somehow try to avoid that the system goes so inevitably to that minimum.
This is the critical question, is how do humans create a new stability domain, a basin of attraction, that we can actually live in? That's the critical question.
Yeah, we will keep on talking. There'll be ways of doing it. A negative contributions here is a way of doing. Adding a cubic term in this expression is also possible. But this expression here depends on this psi. Psi is the difference of temperature between our temperature and the average of the Holocene. So, are there things you can do on the Earth system that depends on cubic temperature, the cube in the temperature? If so, then if you somehow can do that by human intervention, you'll be helping the system to go away from this hothouse scenario. And there are other ideas. For instance, quadratic term is also possible, and we'll be working on all these possibilities. And well, let's see what comes out of that. Well, thank you very much. When you told me yesterday, it was it blew out my mind. Okay, so immediately I went to my pen and I wrote it down, this term. Okay, I even use a trick of mathematics. Okay, I teach general relativity. I call this a metric, and it's exactly a metric because it's symmetric. So well, it shouldn't be negative, but now we are dealing with a new thing, okay? But this is really, really interesting, okay?
I'd like to say that your work has made an important contribution to the discourse around the Anthropocene, hothouse Earth, stabilized Earth. And that's because I think when you look at the observations and the understanding of the individual feedbacks, it's good to have the physical grounding to say that this actually is a sensible, reasonable, possible trajectory.
So let me put two other issues. Well, the first one is that, well, somehow it's very consistent with the research we've been doing ourselves, on which indeed you can build a phase space for a physicist. That's how you predict what the system will do, given the conditions, initial conditions of some type. So when our research points out that there is clearly an attractor, and this attractor is clearly in the direction of your hothouse Earth scenario. So this is also very, very interesting, and it would be, well, very interesting to improve our model so that we have, let's say, a physical understanding of what's really is driving the system towards this situation. The other issue is you have mentioned that there will be the necessity of very, very drastic social and economical changes, and that's one of the reasons you came over for the Casa Común da Humanidade. And so could you tell us something about it, and what are your hopes and expectations concerning this project?
But what do we need to do to get to what we call a stabilized Earth trajectory? And we make the hypothesis that this isn't a natural state of the Earth system, that we're tipping, all these feedbacks are tipping us toward this much more stable, but much more inhospitable state, hothouse Earth. So we humans need to steer the Earth system to a basin of attraction that we might call stabilized Earth. And this is where the common home for humanity comes in. And we have to have the discussion about how deeply do we need to change our present socioeconomic and political system, because it's the system that's driving us extremely rapidly toward hothouse Earth. And the question we face is, can we make sort of slight modifications to the present system, or do we need something more fundamental? And I think the breakthrough that the Common Home for Humanity has made, the concept, is to say that we need to understand not just the physical Earth, the territorial, what is Portugal, what is Spain, what is Australia, what is the ocean in a physical sense. We need to understand the Earth system. In other words, the planet has hardware, which we all know. We've seen maps of the world and so on. But it has software. It has the systems that arise from all the interactions. And this is an intangible thing. It's real, and we feel it all the time through climate. And so we need to understand that humanity now is affecting the entire planetary system. And we need to develop, in the first instance, a legal status for the system, the intangible. And I think the breakthrough is that the legal system has already learned how to do this in different ways. For example, a book that you or I might write, actually the intangible is the idea. It's the intellectual property, as we sometimes say. But that's not a tangible thing. But it certainly is real, because it changes how people think and believe. So we need to work up to the Earth system as an intangible, real heritage of humankind. And I think that simple step is an enormous breakthrough, because then it opens up, how do you manage the intangible, which cannot be divided up by nation states. So this is a conceptual breakthrough that has enormous potential for practical application as well.
Well, thank you very much. We hope that Casa Común da Humanidade, the Common Home of Humanity, is a project that goes forward and has the support of the international community. And we thank you very much for being a main supporter and one of the proposers of this project. Thank you very much.